Hi everyone, this is Daniele Gammelli, and on behalf of my collaborators at Technical University of Denmark and Stanford University, I'll be presenting our work on graph neural network reinforcement learning for autonomous mobility on demand systems. At its core, autonomous mobility on demand aims at bringing together recent advances in autonomous driving technologies with the emerging concept of mobility on demand, whereby customers typically request a one-way ride from their origin to a destination and are served by a shared vehicle belonging to a larger fleet. Specifically, AMOD systems have the potential to enhance the benefits of traditional car sharing and mobility on demand systems by allowing for an automated and centralized control. However, controlling AMOD systems potentially entails the routing of thousands of robotic vehicles within complex transportation networks, which makes the AMOD control problem an open challenge. In the context of urban mobility, transportation networks are naturally defined through graph representations, whereby, for example, nodes represent areas of the cities and edges the connectivity between them, such as in the figure on the right. In this work, in order to exploit the underlying graph structure, we propose the use of permutation invariant computations, such as graph neural networks, to centrally control AMOD systems. Crucially, we argue that graph neural networks exhibit a number of desirable properties and propose an actor-critic formulation as a general approach to learn proactive, scalable, and transferable rebalancing policies. At the high level, the AMOD control problem can be split in two main objectives. First, vehicle dispatching, or concretely, the assignment of idle vehicles to customers requesting for transportation. Second, vehicle rebalancing. That is, for vehicles not matched with any passengers, the operator will either have them stay at the same station or rebalance them to other stations, such as, for example, to anticipate future demand. In this work, we embed the proposed deep RL module within a three-step framework. In the first step, we solve a matching problem to assign available vehicles to passengers with the objective of maximizing total profit at a single decision step. The second step entails determining the desired distribution of idle vehicles by using a learned behavior policy pi. Specifically, given the current state of the system ST, obtained after dispatching, the learned behavior policy will have the task of describing a categorical distribution over stations, indicating the percentage of idle vehicles to be rebalanced in each station, as shown in the highlighted figure on top. Notice how, by doing so, we define a problem where we have an action at each node as opposed to along each edge, as in the majority of literature, thus significantly improving scalability of training and implementation. Lastly, in the third step, we convert the desired distribution computed in step 2 into actionable rebalancing flows by solving a minimal rebalancing cost problem. In this context, our work focuses on devising deep RL agents for step 2 of our three-step framework. We propose an advantage actor-critic formulation where both the policy and value function estimator are characterized by graph convolution layers and optimized to maximize expected profit. On one hand, we devise the output of our policy network to represent the concentration parameters alpha of a Dirichlet distribution. On the other hand, the critic is characterized by an additional global sum pooling layer, thus computing a single value function estimate for the entire network by aggregating information across all nodes in the graph. In practice, we benchmark our methods against both learning-based and control-based approaches on real-world datasets from the cities of New York and Chengdu. We find that our method is able to achieve close to optimal performance in terms of operator profit and customer satisfaction, with significant computational gains when compared to state-of-the-art control-based approaches. In our experiments, we focus on assessing transfer and generalization capabilities of deep RL agents. Specifically, we find agents based on graph neural networks exhibit interesting zero-shot transfer performance. We also find that policies learned through graph convolutions incur only slight performance drop when compared to their fully retrained counterpart. We experiment on tasks like intercity portability, that is, training on one city and subsequently deploying on another city, service area expansion, where we train on a subgraph of the network and later deploy the learned policy on the entire system, and irregular geographies, where, for example, standard CNNs or multi-layer perceptrons would simply be ill-defined. We argue that, without any fine-tuning, the only possibility on effective rebalancing policy to emerge is for the agent to have learned a high-level, abstract, and generalizable understanding of the system dynamics, which we argue is a property enabled by graph-based computations. There are a number of methodological and empirical aspects of this project I didn't get the chance to talk about. Please read our paper or pass by our posters to learn more. Thank you for your attention.